of the session William Missions from Ricardo.
Sorry.
William is a chief engineer working in the heavy-duty diesel engines group for Ricardo UK. He is part of a customer-facing team managing the winning and delivery of engine design and development projects from concept through certification and production. Prior to this role, William spent 14 years working for Perkins Engines in diesel engine product development, and he is a mechanical engineer from the University of Nottingham. So William, thanks for joining the session. William is going to be speaking on the future of low NOx engines, and on the balancing EGR and SCR. William, go ahead. Thank you very much.
Okay, thank you very much. So yes, my presentation today is titled The Future of Low NOx Engines. And really the objective of this is to give a view on the future requirements and technologies to be applied to heavy-duty engines in the future. It is just a view, it's a bit of speculation and a bit of projection about the future. It is just our opinion, and certainly there'll be other views that exist. So after all, we are trying to predict the future here, and as the saying says, prediction is difficult, especially about the future. So it's well known that air quality and emissions are key drivers behind heavy-duty engine technologies, and we're going to be looking specifically at diesel engines here. The presentation is specifically diesel engines. We recognise that in the future air quality and emissions requirements may drive alternative powertrains, electrification, alternative fuels, but certainly within the next coming generation we see diesel to still be a significant proportion of the heavy-duty powertrain, and therefore we're focusing this presentation on that. So I'll look at beyond the current Euro 6 emissions legislation, and we'll take a look at the sort of technologies that might be applied and some of the research that we're doing in that space as well. So before I dive into the core of the presentation, I want to give a bit of background, just a brief overview on Ricardo, really, just to give us some explanation of our experience and give some context to why we're presenting this view. So the company was founded over 100 years ago now by Sir Harry Ricardo, pictured there on the slide at the top, looking very thoughtful. The foundation was in internal combustion engine design, development and manufacture. And some of the very earliest projects that Sir Harry Ricardo worked on himself were focused on improving performance, fuel efficiency and reducing smoke off diesel engines. And in many ways that's exactly what we're doing today, albeit with some more challenging targets, and technologies have advanced since then as well. So over the 102 years the company's grown somewhat, now nearly 3,000 staff worldwide, and we don't just focus on the traditional consultancy of engines and vehicles and transmission design development. We've also covered environmental and strategic consulting, for example. And throughout our history, we've, I guess, focused on delivering these innovative solutions for addressing the global problems of energy, transportation and scarce resources. So let's take a look at the current air quality legislation, current situation and the challenges it presents for the heavy-duty sector. So it's well known that poor air quality is harmful for human health. So within Europe, several thousand deaths every year are attributed to pollutants such as NOx and particulate. So it's a very real problem in the developed world. And it's not just human health that's impacted by these pollutants, but the wider environment as well. Coupled with that, we have the COP21 agreement, which is an international commitment to limit the global temperature rise, and that with that will come some greenhouse gas regulations. Clearly, recent announcements by President Trump to withdraw will have some impact, but let's assume for the sake of this that there's some commitment from the rest of the world to keep going with that. In most cases, these pollutants are principally the product of combustion, so the sources are heating, power generation, and transport. So within Europe, there is air quality legislation in place to deal with this, as we're all aware. So the air quality legislation for Europe has specific local concentration limits for NOx and particulate, and failure to comply with this can lead to penalties. Additionally to this, there's the EU National Emissions Ceiling Directive that places upper emissions limits on the total national emissions for a range of pollutants, and that's expected as well to be further revised in the future for even more stringent reduction. So we've got legislation in place, but let's take a look at, I guess, real data for where we currently are. In this example, you can see measured data, NO2 data from London. And it's clear from this that you can see that the concentration increases as you approach the city centre. In fact, it reaches levels that are in excess of the guideline limits. On closer examination, you can also see that it follows with the road network, and the highest concentrations are measured around busy streets and junctions. So there is a link to transportation. So we know that heavy-duty vehicle legislation, emissions legislation, is in place, but how does it compare to the current air quality legislation for Europe? So in this chart, we've just tabulated the key pollutants that are captured within the air quality legislation and the National Emissions Ceiling Directive, and also some thoughts on future next steps for greenhouse gas regulation. And you can see that on a number of line items, heavy-duty regulation for Euro 6 and Stage 5 does actually address a number of these pollutants. But there's a couple of key gaps, namely NO2, so nitrogen dioxide, isn't specifically regulated for heavy-duty vehicles, and also nitrous dioxide, so N2O, isn't regulated either. So with that in mind, we have a view that future regulation could lead to further NOx reduction and potentially focus on NO2 specifically for heavy-duty vehicles. If we take a look at where the regulation currently is in the US, so the figures here are just translated to milligrams per kilowatt hour for the basis of comparison. But you can see that with EPA 10, the existing regulation, the NOx limit is already lower than it is in Europe. And with the CARB optional levels, they take it to a whole new level. So we have a projection that post Euro 6, we could see some further opportunity for reduction of NOx that would align nicely to the air quality targets also, and possibly some regulation for NO2. There may be other pollutants that also come into play there, whether it's for monitoring or actually regulation stage as well. So taking that on board, we've been considering what technologies may be required to provide the emissions solution for engines beyond that current Euro 6 level, and looking towards that CARB ultra low NOx level. And so I'm going to present some of the ongoing research now. So firstly, I think we need to consider where the key issues currently are. So this is an example of an existing highly regulated engine, so certified EPA 10 engine, running the FTP cycle. And you can see in the top graph there the SCR conversion efficiency throughout the cycle. And it can be seen that once the system's up to its operating temperatures, the average efficiency is fairly high. However, there's key points through the cycle where the efficiency does drop out quite dramatically, and that's in response to the transient nature of the cycle and the ability of the system to deal with the changing exhaust gas conditions. So it gives you some clues to the type of technologies we may need to look at to address that, whether it's better control systems and advanced storing systems. Also within the FTP cycle, similar to the NRTC, the cycle starts from cold, so there's a warm-up period, through which the SCR system isn't able to function efficiently, and therefore there's a risk of higher NOx emissions during that period. So clearly, future technologies that look to reduce that warm-up time would be beneficial, as well as other technologies that may seek to trap the NOx during that cold stage. So there's a broad range of technologies out there, ranging from further reduction of engine out emissions through after treatment and dosing technologies to improve their efficiency, as well as thermal management and controls to deal with the variable nature of the cycle and providing optimum efficiency at any given point. And at Ricardo, we've been researching many of these topics, and we're able to present here some of the, the more promising technologies that we see to provide a solution for the ultra-low NOx levels that we're projecting. I'm going to tease you a bit here, and I'm going to present some technologies that are part of our ongoing research, but it's not at a stage yet where we're able to present the results and the details of the specifications. So it's just a taster, and in the future we hope to be able to present some real results about how these have performed. So firstly, we've looked at an after-treatment system. Takes a more conventional Euro 6 type system of a DPF with SCR and ammonia slip catalyst, but introduces a couple of key new elements. Firstly, we've included an electrically heated catalyst, so similar to the type of product that Watlow have presented at this summit already. And the objective of that system is to using electrical power to heat the exhaust flow prior to the after treatment, such that it reduces the time to heat up the exhaust gas and the SCR to the optimum temperature. There is an energy penalty for providing that heat, but we're projecting that it's actually a very efficient method of thermal management compared to some other methodologies, and it can provide a significant increase in NOx conversion through the cold portion of the cycle. The next new element that we're considering in this case is a lean NOx trap. So this will be used to, in the low temperature conditions, to trap the NOx, and then we'll need periodic regeneration. It has the additional benefit that it also has an oxidation functionality, so it can displace the DOC. The second system we're looking at retains the electrically heated catalyst as well, but now uses a passive NOx absorber. Now this device will store the NOx during the low temperature operation again, and then release it at higher exhaust temperatures. And the benefit of that is that the SCR system is then able to deal with the NOx more efficiently. Again, this has the opportunity to displace the DOC in terms of oxidation functionality. In this case, we're actually also testing it with an SCR on filter rather than a DPF followed by SCR. And this provides the added advantage of bringing the SCR system further upstream in the exhaust and exposing it to higher exhaust temperatures. And the third after treatment system we're looking at is a more conventional, more simplistic SCR-ASC system, but we've closely coupled it to the turbine outlet. So the benefit of that is that it reduces the heat loss prior to the SCR system to reduce the warm-up period, but it requires the urea injection pre-turbine, but that gives the opportunity for excellent mixing of the urea in the exhaust gas flow. This could be a very compact and lower cost system than the others, but obviously may not be the most practical in all applications where it's not possible to closely couple the SCR system to the turbine outlet. Okay, we're also looking at advanced urea dosing systems, which include heated doses, high pressure dosing, as well as alternative geometry doses that seek to reduce the length. I guess the overall objective between these systems is to improve the speed of the hydrolysis reaction, and also reduce the overall system length, again reducing heat loss, so that we can present at higher temperatures to the SCR quicker. So some of these systems that we're looking at here, in building blocks are providing some very high conversion efficiency and potentially some very low NOx outputs. Depending where exactly the next phase of legislation takes us, it may be that the SCR system or the engine and after-treatment package as a whole becomes less reliant on EGR because the SCR system is so efficient. So there's an opportunity to optimize EGR use. I'm sure you've probably seen many charts like this before that show the trade-off between engine out NOx and the fuel consumption, as well as the total cost of fluids. And the general message has always been that the SFC can be achieved as you reduce the EGR and increase engine out NOx. Best total operating cost has to consider the cost of the AdBlue fluid, obviously, and depending on the balance of cost between fuel and AdBlue, the trade-offs always suggested that a moderate level of EGR is optimum. From a CO2 point of view, it generally tracks with the fuel consumption that a lower EGR is also better for CO2. At Euro 6, there are products on the market that don't use EGR, and we've seen a growing trend for that at stage 5 also. Clearly, removal of the EGR system provides some massive advantages to the engine in terms of cost, packaging, reliability. But it has to, I guess, the total system has to be balanced against what the demands are on the SCR system as well. Just one comment we'd like to make through sort of the assessments we've been working on here is around fuel consumption. It's an interesting parameter that maybe isn't so straightforward to give an answer of whether EGR or no EGR is the best solution. Clearly, from a volumetric efficiency point of view, going non-EGR provides some advantages. The question really comes to how efficient your SCR system is and how high the engine out NOx would be without EGR, or whether you need to implement some level of timing retard to control it as well, and therefore do away with some of the advantage you're gaining by not having EGR, as well as how you're going to implement any thermal management and whether that has a greater energy cost than the EGR system as well. So it's a complex piece, and I think we're certainly finding that as cylinder pressures are being pushed higher and higher for the sake of efficiency, the consideration for whether a little bit of EGR gives the best solution for fuel efficiency is certainly there. Okay, so just to take some conclusions. So air quality will continue to be a challenge throughout Europe and the rest of the world, major cities as well as other areas. And post Euro 6, we certainly see there's opportunity for further NOx reduction and specifically NO2 regulation as well. Greenhouse gases will, we expect, become an even greater focus as well. And the type of technologies that we've presented here and forming part of our research, we think will be the building blocks to achieving such low NOx levels for both on and off-highway diesel engines. So with that, I thank you for listening and welcome any questions.
Hi. Yeah, thanks, William. One first question. Sure. You saw those technologies under investigation beyond Euro 6. I'm particularly interested between the one with the lean NOx trap plus SCR or the PNA plus SCR, how do they compare in terms of efficiency and cost as well?
I guess I'm not really able to give an answer to that. So in terms of efficiency, it's I think our simulation has showed promise for both these systems. We're now moving into a test phase, and that's I think where we'll get some real data. But it's just too early for us to actually make a comment on that. Again, from a cost point of view, at this stage of our research, we're I guess steered clear of compromising the solutions we're looking at based on cost. The technologies, some of the technologies we're looking at aren't always fully developed in terms of production, being production ready, and therefore not representative from a true cost point of view at this stage.
Okay. There's one question here. My question, of course, is more like mainly thinking that for passenger cars, when we have LNT, is mainly for when you have a smaller engine, because from the moment the engine becomes a bit larger, then the size of the catalyst would become too.
Okay.
We need to be larger, and then it becomes much more expensive.
Right.
It's more like, but then from the moment you're combining LNT and SCR, would you need a very large NOx trap, or can you go with a small LNT and then SCR for a truck engine?
I guess that's what we're trying to investigate now is with coupling some of these technologies together in terms of things like the heated catalyst to reduce the warm-up period and be less dependent on the NOx trap. So there's some opportunity to, I think, still play that balance and optimize the size of these devices.
Excellent, thanks. Okay. So question over there.
William, as we speculate about the future, I appreciate it's all speculation.
Yeah.
I see you're using a lot of ammonia sensors in your test rigs. Do you see ammonia sensors, OBD, being tied into future generations of heavy-duty vehicles?
So I guess we have a regulation for OBD, for ammonia slip. As we, I guess, push the efficiency of SCR systems harder and harder, there, I guess, could naturally be a requirement for more closed-loop control on that to make sure that we don't breach the ammonia regulation, certainly.
Okay, another question in the middle.
Just a short clarification of the ammonia sensor. There are two OEMs that actually are using it in production today, Volvo not being one of them. And they're using it for control purposes to limit the ammonia slip, to have a maximum conversion without slip. Now to my question to you. Regarding the Linox absorber, then it's crucial that it's empty at next start. But for demanding duty cycles like city bus, how do you avoid that you end the drive cycle with a low temperature period and thereby filling it up before the next start? How do you avoid that situation?
Yeah, and it's an interesting question. At this stage, we're looking at the solutions versus the standard cycles. I think there, as a next stage of the technology development, we need to consider the real-world usage and what technologies how we'd have to address that. But at this stage, we've really been focusing on the legislative cycle only.
Okay, great. Another question here in the front.
Hi, Mihai Drobant with Eaton. Would you care to comment a bit about other alternatives to the get hot quickly strategy things like integration with the engine, closer integration with the engine, and things like perhaps cylinder deactivation or other ways in the engine to keep the exhaust stream hot or get it hot quickly.
So in terms of other thermal management methods, yeah. So there's, I think within the chart you probably saw there's a range of different approaches available. Some of the deac, throttling, heating. So there's advantages and disadvantages throughout. We're looking at this heated catalyst in this particular program because we view that as actually quite an efficient method of delivering that heating function.
Okay. Another.
Okay, regarding that, focusing entirely on the drive cycle, that has turned out to be an historical mistake. If you even though that cycle value is almost half in US, it has been proven by reported by ECCT that they have tested with PEMS, real driving emission, latest version of US trucks and Euro 6 trucks, and it might come to a surprise to you, but it was close to a draw, but the winner was the Euro 6 in real driving emissions, even though that the cycle value is almost twice as high. The real driving emission is slightly superior. Isn't it? Do you foresee that this American system is entirely focused on the drive cycle, as it has turned out not to be as efficient as the Euro 6? Do you see a way that they will stop focusing so hard on the FTP cycle and moving towards real driving emission, because that has turned out to be more clean trucks?
So yeah, apologies. I agree entirely. We're not ignoring the real drive emissions. This is just purely where we are in the development that we've focused so far on the legislative cycle, and we're looking at the the WHTC as well as in terms of our test program. And absolutely, we'd before any the solutions are taken to the next stage of development, we'd be expecting to evaluate them in real driving operation, not just reliant on testbed base. So I agree with your point.
But I mean, if you should fulfill the in-use conformity with a conformity factor 1.5 in Euro 6, when you do that, the VHTC cycle is like a walk in the park.
Yes. Okay.
Okay, another question. Here on the right.
Thank you for the very nice presentation, William.
Okay.
You cleverly see that NO2 is going to be a problem in the future. That's why there will be respectively an emission limit. At the same time, we have seen that NOx have gone down with time and improvements, but NO2 ratio has gone up.
Yes.
Do you see a way to tackle this particular issue?
So sorry, the ratio.
The fact that NO2 is going up. Yeah.
Yeah, and that's specifically why I guess we're speculating that there may be a requirement to regulate both. So NOx, as it is currently at a lower level, plus an NO2 limit to address that in itself. Does that answer your question?
So do you have an approach to control the NO2? In particular, not as a NOx in general, are you going to reduce NO2 rate? Do you see that it's going to be
I see in terms of the ratio. I guess the technologies we're looking at here are looking at reducing NOx as a whole, and therefore you get the benefit of NO2 as a fraction reduction as well. But within the detail of this, we also need to consider what's happening in terms of NO2 creation within the oxidation element of the catalyst, and whether that is producing a higher ratio. So we've suggested thought about a limit here where it's a 50-50 split, that seems a reasonable sort of level that you could achieve with this type of technology.
Great. Thanks. Any final questions for William? One at the back.
Thank you. I think the gentleman down there, I think, had the same sentiments. This does seem to be getting more and more removed from real-world driving. Can you maybe comment? Do you see any of this really helping the current problem? We have an issue with Street Canyon NO2. What we're doing is we're putting on technologies which will improve the NOx emissions during a period after, if you've had a controlled 20-minute cool down. The difference, if it's longer or shorter, might be a totally different result. I don't see, Alan Tolley there was saying very much, we should be having a much more holistic approach to this stuff. Mm-hmm. I'm concerned that we're just going still further down the same hole.
So I guess the one comment I have is that, I guess it echoes maybe something that's said already, that with Euro 6, what we have seen is that Euro 6 compliant engines in the real world, measured with PEMS, are actually complying very well. So we think for the first time the regulation is in a position where it is addressing real driving, real world emissions well, and so we're just projecting next step of reducing those levels further, but maybe there's other conditions, cycles that need to be considered also. Yeah.
Great. And we do have time for a final question here in the front. Max coming.
Speculation's great fun, isn't it? There's no right or wrong answers. Formaldehyde in Europe, William. What's the Ricardo view?
Oh, you've got me there. So we think there is I guess, a likelihood that other compounds are going to be regulated, including aldehydes within that. I don't have a clear answer on what likely probability of that is and what the limits are likely to be there, unfortunately.
Great. So had some very interesting questions. Thank you very much, William, for joining.